Let me explain our project. The theme is enhancement of PUF-based remote keyless entry system using machine learning techniques. Here is the overview. First, let's talk about the background. Our research focuses on improving the security of communication between the cards and the key fobs. In recent years, this communication has been exposed to risks such as replay attacks and logjam attacks. Introducing the step of a logjam attack. Initially, the user sends the unlock communication to the card using a key fob. At this point, the attacker jammed the communication, temporarily storing the jammed unlocked signal. Since the jammed signal doesn't reach the card, the user, unaware of the interference, sends the unlock communication to the card again. The second unlock communication, which is not jammed, successfully reached the card, unlocking it. At this point, the logjam attack is succeeded. The attacker can use the initially jammed unlocked signal at any time to unlock the card. This is essence of the logjam attack. Our goal is to enhance the security of communication between the key fob and the card, preventing replay attacks and logjam attacks. Especially, we aim to improve the safety of key fob and the card communication to prevent the replay attack and logjam attacks. Next, let's discuss our architecture and the equipment. Starting with the overall architecture. When the user sends the unlock communication from the key fob to the card first performs signal detection upon receiving the communication. If the communication is deemed to be from attacker during a signal detection, it is blocked immediately. If it is determined to be normal, the system enters a PUF session. During the PUF session, after multiple communications, user authentication is performed by comparing the data. Only if all communications are deemed safe will card unlock. Let's explain into the detail of signal detection. We use the CNN in machine learning for signal judgment, divided in two phases: the training phase and the attacker detection phase. In the training phase, signals collected in advance are useful to train the machine learning model. Subsequently, in the attacker detection phase, newly received signals are compared with the model created in the training phase to determine whether it is from a user or attacker. The HODOR is a device used for observing communication signals, allowing you to monitor communication in the frequency range of 1 MHz to 6 MHz. I use this equipment to capture and analyze the communication signals of a card and the key fob. By leveraging machine learning, I create a model based on these signals for signal detection. Next, we replicate the actual communication between the card and the key fob using a Raspberry Pi. The communication signal utilizes the 433 MHz bandwidth LoRa technology. LoRa involves the dedicated transceivers for sending and receiving signals. Additionally, these transceivers require a special antenna to facilitate communication. Here is a basic list of equipment. For both card and the key fob, there is one set each of a Raspberry Pi and the other fruit LoRa and cable and antenna. Additionally, for signal observation and the storage purpose, we have the HODOR along with a dedicated antenna. We use this equipment for our machine learning task, which include the Intel CPU and the NVIDIA GPU and the Ubuntu operating system. Here we capture data with the HODOR after preprocessing it and create a model using convolutional neural networks. This is a list of equipment for machine learning. We use the GeForce RTX 4090 for the GPU, enabling a powerful parallel processing capabilities. A powerful ZPU requires a sufficient power supply, for which we have a 1200 watt power supply. Lastly, to address a concern about the ZPU being too large to directly mount on the motherboard, we have prepared a dedicated cable to connect the ZPU and the motherboard. Next, let's discuss the PUF session. The PUF session is divided into two phases, the registration phase and the authentication phase. In the registration phase, the characteristics of the car and the key fob devices are pre-registered. Upon receiving a new communication, the authentication phase begins. During this phase, communication takes place based on the data registered in the registration phase, and data matching is performed. If all communication are completed and deemed safe, the car unlocks. Next, we will proceed with the demonstration of the car and the key fob. The program utilizes the SSH to access and execute a Python script remote to both the car and the key fob. Initially, the car program is launched, followed by the waiting for communication from the key fob. Upon the initial of communication from the key fob, success is confirmed if the car received unlock at the final signal. Lastly, let's explain the timestamp. The timestamp is included in the PUF session, especially during the message 3 of the PUF session. The time and the key fob send the communication and the time the car received the communication are compared. This comparison triggers the predefined process. Adding this feature ensures that even if the last communication of PUF session is jammed, it times out when the communication is recent, enhancing the security. Additionally, if it is the attacker's communication, unnecessary process is avoided, reducing the processing time. Here is a list of equipment we have purchased. The equipment serves a different purpose, mainly catering to machine learning and PUF applications. Notably for machine learning, we invested in a ZPU to enable high-precision machine learning processes. Let's move on the result of our experiments. The accuracy of machine learning signal detection and the train loss improves with the increasing number of epochs, achieving higher accuracy and a lower train loss. Next, regarding a system execution time, the results show 1.3 seconds for machine learning alone, 2.01 seconds for machine learning combined with PUF, and 2.05 seconds for machine learning combined PUF and the timestamp. Our research results have been added to GitHub, and they can be accessed online anytime. Additionally, a README file provides an explanation on how the code is utilized for different applications. If you're interested, please feel free to visit our website and explore the details. Finally, our research has been dedicated to enhancing the security of communication between the car and the key fob. We look forward to the continuous improvement and the evolution of our research, with the aim of contributing to society in meaningful ways. With this, we concluded the explanation of our project. Thank you.